Ever wondered how data zips through computer networks at lightning speed? In Chapter 1, we delve into network models, unraveling the intricate pathways data takes from point A to point B. Picture this: your email flying through cyberspace, hopping from server to server in a blink. It's a digital dance orchestrated by complex algorithms and protocols. Stay tuned as we uncover the secrets behind this technological marvel. Let's begin our journey into the fascinating world of network communication. Today, we embark on a journey through the intricate world of networking. We'll delve into network layer models, where OSI and TCP/IP frameworks serve as the backbone of communication. As data traverses through layers, we uncover the fascinating process of data encapsulation, revealing how information is carefully wrapped and unwrapped. Delving deeper, we tackle the concepts of MTU and fragmentation, shedding light on packet sizing limits and data segmentation. Then, we navigate the realm of latency versus throughput, deciphering the nuances of speed metrics and their practical implications. By the chapter's end, you'll grasp the essential principles governing data flow across networks, from your device to servers worldwide. In this exploration, we strive to captivate your interest with intriguing insights, maintaining a dynamic rhythm of concise points and brief explanations. Let's set sail into the realm of networking intricacies, where each concept unravels new layers of understanding, culminating in a profound comprehension of data's intricate journey through the digital landscape. Ever wondered how data seamlessly flows from your device to a distant server? The world of computer networks can be a labyrinth without a guide. Enter network models, the solution to this chaos. These models dissect communication into manageable layers, akin to an assembly line in a factory. Each layer has a specific role, simplifying understanding, design, troubleshooting, and upgrades. Picture unraveling the journey of an email, from keystrokes to screen, layer by layer. With network models, complexity becomes clarity, and chaos transforms into order. In the world of network communication, the OSI model reigns supreme, dividing the complex web into 7 distinct layers. Picture a hierarchy of services, each layer supporting the one above it and relying on the one below. The upper layers, including application, presentation, and session, handle user interfaces, data presentation, and connection management. Moving down to the middle layers, transport and network take charge of reliable delivery and efficient routing. At the base, the lower layers, data link and physical, control hardware addressing and the physical transmission of data. From user services to physical transmission, the OSI model orchestrates seamless communication. Ever wonder how data travels through the intricate layers of the OSI model? At the foundation lies the physical layer, where raw bits traverse via various mediums like cables, fiber optics, and Wi-Fi. Moving up to the data link layer, it's all about efficient node-to-node communication using MAC addresses and protocols like Ethernet and Wi-Fi. Next, the network layer takes charge, routing packets across networks using IP addresses to find the optimal path. Ensuring reliable end-to-end delivery, the transport layer employs TCP for accuracy and UDP for speed. The session layer orchestrates connections between applications, managing dialogues and synchronization. Then, the presentation layer steps in, translating data, encrypting, and ensuring readability through format handling. Finally, the application layer brings it all together for users, with protocols like HTTP, SMTP, and FTP catering to web browsing, email, and file transfer needs. Each layer plays a vital role in the seamless flow of data, from raw signals to user-friendly services. Ever wondered what's behind the seamless functioning of the internet we rely on daily? Enter the TCP/IP model, the powerhouse of online connectivity. Unlike the theoretical OSI model, TCP/IP, developed by the U.S. Department of Defense, streamlines the process by condensing 7 layers into just 4. Picture this: the application layer merges OSI layers 5 to 7, the transport layer aligns with OSI layer 4, the internet layer corresponds to OSI layer 3, and the network access layer combines OSI layers 1 to 2. This practical model focuses on real-world network protocols, laying the groundwork for modern internet communication. It's not just a framework, it's the very backbone of our digital interactions. Ever wondered about the OSI versus TCP/IP models and how they stack up side by side? The OSI model boasts 7 layers, offering a more detailed breakdown for a conceptual understanding. It's protocol independent, focusing on functions rather than specific implementations. In contrast, the TCP/IP model features 4 practical layers, emphasizing real-world protocols like TCP and IP. While OSI is the go-to for troubleshooting, it's a Layer 3 problem. Network engineers implement TCP/IP protocols in practice. Both models play crucial roles in comprehending network architecture. Ever wondered how data traverses the vast network landscape? Enter encapsulation, the art of wrapping data with protocol information at each network layer. Picture it as a letter traveling through the postal system. Each stop adds a new layer of addressing and packaging. As data descends from the application layer to the physical layer, each level contributes its header and sometimes a trailer, housing essential control details. This nesting process forms a tiered structure where each layer's data unit envelopes the previous layer's complete package. Encapsulation, like Russian nesting dolls, illustrates this concept beautifully. Each layer wraps the former's data with its own informational envelope. In essence, encapsulation safeguards and organizes data as it journeys through the network's intricate layers. Ever wonder how your "Hello, world" message goes from your screen to a friend's inbox? It's all about the encapsulation process, where each layer plays a crucial role. At the application layer, you craft your message, while the transport layer adds headers with port numbers. Moving down to the network layer, IP addresses are included, and at the data link layer, MAC addresses and error-checking codes become part of the frame. Finally, at the physical layer, your message is converted into electrical signals or light pulses, ready to traverse the medium. Each layer meticulously prepares your data for its journey. Ever wondered what really happens behind the scenes when you hit enter after typing a website into your browser? Let's unravel the layers of encapsulation as your request travels through the digital realm. Your journey begins with the application layer, where your browser crafts a GET-request4/index.html. As this request dives into the transport layer, TCP adds crucial information like source and destination ports. Moving down to the network layer, IP addresses come into play, guiding your request to its intended server. Down the line, at the data link layer, Ethernet frames provide the physical addresses needed for the data to navigate through the network. Finally, at the physical layer, your digital request transforms into electrical signals racing through cables towards its destination. Upon arrival, the de-encapsulation process reverses this journey, with each layer shedding its header to process and forward the data. In essence, encapsulation serves as a digital envelope, protecting and guiding your data through the vast expanse of the Internet. Ever wondered how data travels through networks? Enter protocol data units, or PDUs. From the raw message at the application layer to bits on the wire at the physical layer, each step has its own PDU name. Think of it like a Russian nesting doll of data encapsulation. If a packet gets dropped, you'll know it's a network layer issue. Understanding these PDUs is like having a map for troubleshooting network woes. Data becomes a segment, then a packet, a frame, and finally, bits, all on a journey through the OSI model. Remember these names, and you'll decode network mysteries with ease. Ever heard of MTU? It's not a new trendy acronym, but rather the maximum transmission unit, the size limit for packets traveling through a network. Picture it as the maximum size a delivery package can be. Different network types have varying MTU sizes. Ethernet tops out at 1,500 bytes, Wi-Fi typically at 2,304 but often set to 1,500, and PPPoE at 1492. Data centers can handle jumbo frames up to 9,000 bytes. Keep in mind, the MTU also includes headers, leaving less room for actual data. So, for a 1,500 byte Ethernet MTU, only around 1460 bytes are available for data transmission. Remember, when it comes to MTU, size does matter. Ever wondered how data bigger than your network's limit gets through? Meet packet fragmentation. When data exceeds the MTU, it's sliced into smaller packets at the IP layer. Picture this, a 3000 byte packet meets a 1500 byte MTU and splits into 3 fragments. Each fragment gets its own IP header, helping in reassembly at the destination by using ID and offset. But here's the kicker: lose one fragment, and the whole original packet needs a redo. That's why sending correctly sized packets from the start beats the hassle of retransmission. Remember, in networking, size does matter. Ever wondered how data packets navigate the vast network landscape without getting fragmented? Enter Path MTU Discovery, a clever technique that scouts out the smallest maximum transmission unit, MTU, along the entire source-to-destination path. Here's the magic: the source sets the don't fragment flag, and if a router encounters an oversized packet, it simply drops it. The router then sends back an ICMP fragmentation needed message, prompting the source to adjust the packet size and retry until a smooth, fragmentation-free flow is achieved. This process unveils the Path MTU, ensuring seamless data transmission. Modern TCP implementations handle this dance automatically. In a nutshell, Path MTU Discovery saves the day by finding the optimal MTU size for efficient data delivery. Ever wondered how network performance is truly measured? Let's delve into the world of performance metrics. Latency and throughput are key players here. Latency measures the time it takes for data to travel from point A to point B, like calculating a flight's duration. On the other hand, throughput focuses on the amount of data transmitted in a given time frame, akin to determining how many passengers an airline can move per hour. Understanding these distinctions is vital for troubleshooting network issues and shaping effective design strategies. So, how do we balance speed and capacity in network performance? Ever wondered what causes that split-second delay when you're online? Let's break down the components of latency. First, there's propagation delay, the time it takes for a signal to travel through a medium. Next, transmission delay is the time to push all packet bits onto the wire. Then, processing delay occurs as routers and switches determine where to forward packets. Finally, queuing delay happens as packets wait in line at routers. These factors contribute to varying latencies, from lightning-fast local networks to the slower pace of intercontinental connections. Video calls, online gaming, and real-time trading are just a few applications affected by latency. Remember, when it comes to data transmission, every millisecond counts. Ever wondered how data zips through the digital realm at lightning speed? Throughput holds the key. Picture this: at the theoretical max, your network flaunts its 1 gigabit per second prowess. But in the real world, typical throughput takes a hit, battling protocol hiccups and network traffic. Come the chaos of congestion, and throughput plunges. Bandwidth, congestion, protocol overhead, packet loss, these are the gatekeepers of your data flow. Imagine video streaming, hefty file transfers, and cloud syncs relying on high throughput to thrive. In this digital dance, the faster the beat, the smoother the groove. In the dynamic realm of network optimization, a critical balance teeters between latency and throughput. Picture this: a tug-of-war between swift responsiveness and data-dense speed. Low latency takes the lead, ideal for interactive realms craving quick exchanges through nimble, small packets on direct paths. Yet, it may fumble some throughput for that instant gratification. On the flip side, high throughput reigns supreme for hefty data hauls, relishing large packets and buffered processing. The trade-off? A bit more patience for a flood of information. But hold on, a balanced approach emerges as the unsung hero, juggling diverse workloads with finesse. Quality of service, traffic prioritization, and adaptive algorithms join forces for the ultimate optimization dance, catering to varied application needs simultaneously. So, in the dance of latency and throughput, aim for harmony, not discord. Imagine our network as a bustling highway system, where latency is the trip duration and throughput is the highway capacity. Just as longer routes and slower speeds increase latency, more lanes and smooth traffic flow boost throughput. Picture a fast, narrow highway versus a slow, wide one. The balance between latency and throughput is key. So, how can we optimize our network for both speed and efficiency? Let's explore further. Ever wondered how network communication is streamlined? Network models like OSI and TCP/IP break it down into manageable layers, each with specific roles. As data travels through the stack, encapsulation adds headers, creating nested PDUs. The MTU sets the max packet size, with path MTU discovery aiding in avoiding fragmentation. Latency measures delay, throughput measures capacity, crucial balances in networking. In Chapter 2, we'll delve into TCP, UDP, and IP, applying these concepts practically. Teach a friend to solidify your grasp. Networking, a world of organized complexity, encapsulated data, and crucial trade-offs.